So welcome back to this channel. So we are going to be starting organic chemistry with this video. So this video is presented to you by Yusuf, and your advice to subscribe to the channel and you like the video so that it can be promoted to your fellow students. That organic chemistry is going to be a branch of chemistry that's going to deal with the study of compounds that are largely containing carbon. So you're saying that these compounds are going to contain carbon combined with one or more elements, especially hydrogen and oxygen, though we have some bit of nitrogen. But basically, the major element that we are going to be looking at in this branch of organic chemistry, which is organic, is going to be dealing with carbon. Now, carbon combines with other nonmetals like hydrogen, oxygen, and nitrogen. And after combining with those non-elements, we give them specific names, as you are going to be covering one by one. So we are going to start with uniqueness of carbon, and we are saying that carbon has the ability to form a variety of chains. Now, formation of a variety of chains is called catenation. In other words, catenation refers to the ability of carbon to pair up with its fellow carbon atoms. When you see a long chain of carbon atoms, it's only carbon element that can do this. There's no other element that can do such an activity. So catenation refers to the ability of carbon to form a long chain of its individual atoms. And we are saying that this is going to be the ability of similar atoms to form long chains, and it's only carbon that has the ability to do that. Now, when you're looking at inorganic chemistry, this was mentioned as one of the abnormalities carbon has under group 4 elements, which make it to be unique. Now we are saying that other elements can catenate, for example sulfur, silicon, boron, and some other metals, but this is on a very rare case. It's only carbon that has numerous compounds, where it forms numerous bonds between its individual atoms to form long chains. Now formation of long chains with the same atom is what we call catenation. So catenation is simply the ability to form a long chain from the similar atoms of an element. If you go to part B, we are saying that also carbon is unique by having the ability to form bonds which are nearly equal in stability with other nonmetals such as hydrogen, nitrogen, oxygen, and other halogens. Through hydrogen, we are saying that though hydrogen is electropositive and the rest are going to be electronegative. Now, to shorten up this sentence can also mean that carbon has the ability of forming bonds with other nonmetals, unlike any other element. If you look at carbon can combine with nitrogen, and there are very few nonmetals that can do that. It's only carbon as a nonmetal that can combine with other nonmetals, so that makes it unique. So you're saying that carbon has the ability to combine with other nonmetals, and you have said that those nonmetals, we are going to see nitrogen, we are going to see oxygen, and we are going to see other halogens as we proceed in this video. Now we are also saying that carbon has the ability to form 4 bonds leaving no unpaired valence electrons. Now when you're looking at inorganic chemistry, we told you under group 4 that carbon does not show inert pair effect, implying that all its atoms engage in bond formation. That's why we are saying that carbon has the ability to form 4 bonds, leaving no unpaired valence electrons. So it simply means that, to shorten this sentence up, we can also say that carbon does not show inert pair effect. Remember, as a reminder, inert pair effect, we said, is the inability of the outermost ns2 electrons to participate in bonding under group 4 elements. So carbon does not show inert pair effect is another meaning for this sentence. If you go to part D, carbon has the ability to form multiple bonds with itself and with other atoms. This statement you are meaning that you are going to say that carbon has the ability to form double bonds. Carbon also has the ability to form a single bond. Carbon also has the ability to form a triple bond. So this formation, this ability to form these multiple bonds is what makes it unique. There's no other element that forms multiple bonds. So carbon is unique in that it is going to be forming multiple bonds between atoms of its element or other non-metals. At some of the terms that you are going to be using in organic chemistry. Now, first of all, we are going to start with homologous series. Now, you're saying that homologous series is going to be a group of organic compounds, but these organic compounds are going to be the same general formula. But what's going to vary? But they are going to vary only by the next methylene group. Now, the methylene group is represented by CH2. This is very different from the methyl group. So these compounds are compounds of the same general molecular formula, but they only differ from each other by a methylene group. So when you have asked you for this definition, what you want you to say is that you talk about a group of organic compounds that are going to have the same general formula, but they are going to vary from each other by a methylene group. And the examples you have given here, we have given you alkanes, alkenes, alkynes, alcohols, among others. Now here, we are going to talk about each of these elements as a topic, still on this channel and in this playlist. So this playlist is going to be for organic chemistry purely. Now if you look at part B, we are going to look at a functional group. Now you're saying that a functional group is going to be an atom or a group of atoms which are going to determine the chemical properties of the homologous series we are dealing with. So whenever we are talking about functional group, just know that that's going to be an atom, either an atom or a group of atoms that's going to determine the chemical properties of a given compound or a given substance. So the main thing here is that you talk about group of atoms or an atom that determines the chemical properties. You can either say of a homologous series or you can say of an organic compound. What you want to see here is that the main function of a functional group is that it determines the chemical properties of that substance or organic compound. Now let's also look at the radical. And you are saying that a radical is going to be an atom or a group of atoms with unpaired electrons. Now the way we write a radical, we write it with just one unpaired electron, which is represented by a dot. And that dot we put it upwards on an atom or a methyl group. Like if you see here, this is a methyl group, and you place this dot here. Let me hope you see it according to the resolution you're using to see this video. There's a dot here, upwards this carbon atom, and that dot is to represent that this methyl group is a radical. So represent a radical by writing an atom and putting a dot upwards on it, to show that a radical is an atom that has only one unpaired electron. So that's why you're saying that an atom or a group of atoms with unpaired electrons. This is not supposed to be electron, it's supposed to be with unpaired electron. It is represented by a single dot. So that's going to represent a radical. If you look at this atom of chlorine, we also placed a dot here. Any atom having a dot upwards is going to be a radical. Now we are going to be looking at the reactions under which such radicals are being formed. Then what about a mechanism? If you are to define a mechanism is going to be the stepwise exposure of the path taken by both the reactants and intermediates towards forming products. So in other words, a mechanism is going to show you the detailed steps under which a reaction is taking place. It shows you how a reaction comes to give you products. It's like a step-by-step procedure that if you are reacting an alcohol with an alkene, this is what happens. So that's the meaning of mechanism. It's a stepwise exposure of the path taken by both the reactants and intermediates towards giving products. Now we are saying that here we have given you a table showing the homologous series and then the functional group. I told you the functional group determines the chemical properties of that organic compound or of the homologous series. Now the homologous series is a group of atoms or group of organic compounds that can be differentiated by a methylene group, which is represented by CH2. Now alkenes have this general formula. Now it's very important to know the general formula of alkenes, the general formulas of these three, because these ones are very commonly set. We set them in questions involving calculations, and it will require you to memorize this formula so that you can get the value of N and you find the molecular formula. So always remember that. These first three, you must memorize them. You may forget these ones if you want, but these first three, you must memorize them. So you're saying that alkenes, the functional group in them is going to be the hydrogen atom. Now the alkenes, the functional group is going to be the carbon to carbon double bond. Now sometimes we ask you for the functional groups in questions, especially paper 1. This is how you're supposed to present your functional group. You either present it like this, or you tell us that it's going to be a carbon to carbon double bond. If you look at alkynes, it's represented by a carbon to carbon triple bond. We have bonds this side. You make sure that you include those bonds sideways. So those carbon to carbon triple bond indicates alkynes. And the other ones, X is going to, now usually in organic chemistry, whenever you see an X, we are going to be representing an halogen. And when I talk about halogen, I'm talking about group 7 elements, where we have fluorine, chlorine, bromine, and iodine. Now the OH group is for alcohols. Whenever you see OH groups attached to any organic compound, always remember that that is an alcohol. Now this is like a map. Whenever you see a compound having this structure, that's a carboxylic acid. And for this one, it's going to be an ester. Now this one is like a map to organic chemistry. The moment you fail to understand this table, you are going to have inconveniences as we proceed. So I've told you this is a carbon to carbon double bonds, and what does it indicate? It indicates that that compound is an alkene. When you say carbon to carbon triple bond, it means that that compound is an alkyne. When you see an X attached to a compound, just know that that compound is an alkyl halide. Halide comes from halogens. Halogens represent elements in group 7. When you see OH attached to a substance, just know that it's an alcohol. And when you see this one attached to any compound, you have to know that that's a carboxylic acid. Similar to this, being an ester, but these ones, for the case of senior 5s, these ones should be on your fingertips. Proceed with the table. Now we shall be getting into details as we go on with your chemistry, and you understand them better. This represents an aldehyde, this represents a ketone. Now this represents an amide. Amides have the carbonyl group, and they also have the methylamine group, or the amino group. They have the carbonyl group and the amino group. So amines have the amino group. So the difference between amines and amides is that amides have both the carbonyl group and the amino group, but amines have only the amino group. Esters have the O in between their compounds. So let's look at what an electrophile means. Now this is very important. An electrophile refers to a species that is in need of electrons, or we shorten it by saying it's going to be an electron deficient species. Now, which sign should any atom or group of atoms carry when it is in need of electrons? If you look at the principle of charges, like charges repel each other and unlike charges attract each other. Remember that electrons are negative. So if electrophiles need of electrons, that means that our electrophiles here are always going to be positively charged. That's why we are saying that electrophiles are going to carry a positive charge. That's why whenever you see this atom carrying a positive charge here, that is an electrophile. It is an electron deficient species. Or you can say it's a species that is in need of electrons. Since electrons are negatively charged, it must be positively charged such that it can attract those electrons towards itself. So an electrophile is an electron deficient species, or is a species that is in need of electrons. Protons are also in need of electrons because they are positively charged. That means that they will attract electrons towards themselves. Now we are saying that neutral electrophiles carry no charge, but ignore this. So we are saying that all electrophiles attack sites that are rich in electrons. I've already told you they are positively charged. That means that they are always going to look for negatively charged components, and which are going to be electrons. So what we should remember is that electrophiles are species that are positively charged, hence they are going to be looking for electrons, or they are going to be looking for sites that are negatively charged, or they are going to be looking for sites that are rich in electrons. That's why we define them as electron deficient species. They lack electrons, but they are looking for electrons. But the neutrophils, now the neutrophils are the opposite of electrophiles. We are saying that the nucleophils are going to be electron-rich species. That means that for them they are going to be carrying a negative charge. Now once they are carrying a negative charge, that means that they are going to be donating electrons. They are neutrophils, they are rich in electrons. That's why they are negatively charged, because electrons are negatively charged. So for them, they are electron-rich species. That means that they can easily donate electrons that electrophiles are looking for. That's why we are saying that negative nucleophiles have an electron pair, and they are always negatively charged. Like the bromide ion, we have a negative charge here, and the cyanide ion, where we have a negative charge here. Now we are saying that neutral nucleophiles have a lone pair of electrons, but you can always ignore this because it's going to come later. So what you should take here is that nucleophiles, they are electron-rich species, hence they are looking forward to donate electrons, whereas that means that they are going to be negatively charged because electrons are negatively charged and they contain more of electrons. Now let's look at the definition of a carbocation. Now we're saying that a carbocation is going to be that substance in which the carbon atom carries a positive charge. Now you should understand this one very well. For something to be a carbocation, it must be a carbon atom which is attached to alkyl groups. Now when I talk about alkyl groups, for this moment you are going to say that is attached to other elements or group of atoms. But that carbon at the same time, it carries a positive charge. So that makes it a carbo. Carbo is from carbon, and cation means that it's going to be positive. So carbocation. That's why we are defining it as a substance in which the carbon atom is going to carry a positive charge. Now you're saying that the stability of the carbocations is going to increase in this order, whereby the tertiary carbocation is going to be greater than the secondary carbocation and it's going to be greater than the primary carbocation. Now tertiary, we represent it by 3 degrees. So whenever you see 3 degrees anywhere, just know that we are talking about tertiary compound of any element or of any compound you are dealing with. So 3 degrees represents tertiary, and 2 degrees represents secondary, and 1 degree represents primary. So that's why we are saying that primary carbocation has only one alkyl group. An alkyl group refers to the group that is attached to the carbon atom that is positively charged. Alkyl group is anything that is attached to a carbon atom that is any group of atoms or an atom that is attached to a carbon atom, that in this case that is going to be positively charged. So if you look at these down examples here, we have this, our positively charged carbon atom is here, and what is attached to it is this group, which is called the methyl group. So this is our alkyl group. So it's going to be the group that is attached to the carbon carrying a positive charge other than hydrogen. So if you look at 2, I've told you 2 degrees is going to represent secondary. So secondary has 2 alkyl groups, and this is the one. This is our positively charged carbocation, and it's attached to hydrogen. We don't count it, we only count the carbons it is attached to. If you look at this one, it's attached to this group and this group. That makes it a secondary carbocation. And with a similar explanation, this is going to give us the 3 degrees carbocation. So 3 degrees represents tertiary. So this is a tertiary carbocation. We are going to look into those into more details, but what we should focus at is understanding everything in this video. Groups attached to the carbon atom carrying the positive charge. For example, this. Let's look at also the following terms. Now we are going to be looking at saturated compounds and unsaturated compounds. Now what is a saturated compound? You have been hearing this term all along. But in organic chemistry, whenever I see saturated and unsaturated, we are talking about bonds. So anything that's going to be saturated, it must have one carbon-to-carbon bond. Saturated means you must have one carbon-to-carbon bond. But unsaturation is going to mean that your element or the organic compound you are dealing with has either carbon-to-carbon double bond or carbon-to-carbon triple bond or more than that. So you're saying that's why we are saying that a saturated compound is going to be a compound with only one carbon-to-carbon single bond. For example, as we are going to look at it in alkanes. And we're saying that unsaturated compound is going to be a compound with a carbon-to-carbon either double or triple bond, for as long as the bond we are having in that element is going to be greater than 1. So it's going to contribute our unsaturated compound. And the examples we can look under that is alkenes and alkynes. However, also benzene can be added. We shall see benzene later in the videos. Now what is an aliphatic compound? Now these ones are the very good ones that you also need to understand. Now what you should, whenever you see the word aliphatic, I want you to think about just a linear chain of compounds. That's what we mean by aliphatic. It's a straight chain, or anything represented in a straight format. But aromatic, whenever you see the word aromatic, know that we have a benzene ring in that compound. So aromatic means that there are a lot of unsaturated bonds within that compound, and we only have those bonds in benzene ring. So that's why to define those definitions, we are going to say that an aliphatic compound is going to be a compound in which carbon atoms are going to be joined in a straight chain or branch chains, but for as long as we don't have a benzene ring there. Now the moment we add a benzene ring to such compounds, we form what you call aromatic compounds. Because benzene is very rich in unsaturation, that's why we call it an aromatic compound, and the only aromatic compound we have is benzene. So anything attached to benzene ring becomes an aromatic compound. So you're saying that an aromatic compound is going to be that compound with a benzene ring in its structure. For example, benzyl chloride, which is given by this formula. Let me hope you are able to see it. This is how we draw the benzene ring. Now we talk about another important subheading of isomerism. Now, definition of isomerism is very important because we examine it often. Isomerism is simply, just like you studied allotropy in O level, is similar here, but it varies in a certain way. But here we are going to be saying that isomerism is going to be the existence of two or more compounds, but these compounds are going to be having the same molecular formula, but they are going to differ in their structure, formula. It's as simple as that. Existence of two or more compounds with the same molecular formula, but they differ in their structural formula. This isomerism is going to exist in compounds that are going to have the same molecular formula, but they are going to differ in the way we present their structures, as we are going to be looking at it. Now we're saying that such compounds are going to be called isomers. Now let's look at the types of isomerism. Now we are saying that isomerism exists in two main types. We have what we call structure isomerism, and we have what we call stereoisomerism. Now under structure isomerism, we also have categories, which is divided into three. Also stereoisomerism is divided into two. And let's look at that. Looking at the first type, we are going to be looking at the structural isomerism. Now we are saying that structural isomerism is going to be that isomerism when two or more compounds that are having the same molecular formula but different structural formula exists in isomerism. In other words, it's a type of isomerism when two or more compounds having the same molecular, they have the same molecular formula but they differ in structural formulae. And you're saying that structure isomerism has only, now there are mainly three classes. And let's look at them. The first class is not four, there are mainly three. The first class is chain isomerism. Now as you are hearing the word chain, I've told you they have the same molecular formula, but they are going to define structure. Structure is the way you are presenting. The molecular formula is the way you get it when you in your O level. You also repeat it here when you put your N and equate it to molecular mass. That's the molecular formula you get, but the way we present this in terms of structure is going to be like this. Now this is a molecular formula. They have the same molecular formula, but they are going to differ in structures. So both of these compounds, hexane and 3-methylpentane, have the same molecular formula, which is this, but they are going to differ in their structures, which is this. So this is the molecular formula, and this is the structural formula. Structural formula is how we present them visually. So you're saying that chain isomerism is going to be when two or more, it's going to happen when two or more compounds are having the same molecular formula, but they are going to differ in the arrangement of the carbon atoms. Now this one is going to give rise to branched chains and unbranched chains. When you talk about unbranched chains, is like hexane, where you are not seeing any branch deviating away from that compound. But for a branched chain, you are going to see branches like this one deviating away from that compound. Now if you count the number of carbon atoms, they are going to be the same as the number of carbon atoms here, and similar to hydrogen atoms. But what's going to vary, what's varying, is the way the carbon atoms are arranged. So this structure is very different from this one, but both of them are having the same carbon atoms and the same hydrogen atoms. Now maximally, carbon must have 4 bonds. That's why it is attached. This is the first bond, and this is the 3 hydrogen bonds it's attached to make them 4. And each carbon here is the same. So the variance in structure, in their chains, or variance in the arrangement of carbon atoms in the chains, contributes what we call chain isomerism. Now this is called hexane because hexane, X is coming from 6, and we name it with prefix ANE. Now we are going to be looking at this naming under alkanes, and we are going to be looking at nomenclature on how to name every compound there, which is going to be the next video. So this is going to be 3-methylpentane. Looking at position isomerism. Now as you're hearing the word position, is another type of structure isomerism, and we are saying that this is going to be when two or more compounds with the same molecular formula and functional group but are going to differ in the position of the functional group. Now here, this is not supposed to be with the same molecular formula and it's supposed to be same molecular formula but different. Okay, yeah, it's supposed to be, This position isomerism is going to occur when both the compounds you're dealing with, they're having the same molecular formula and they're also having the same functional group, but they are going to differ in the positions where the functional group is located. If you look at these two compounds, they have the same molecular formula. This is called the molecular formula. But if you bring their structure formulas, what's going to vary? The functional group here is OH, and when I told you in your map of the homologous series we looked at, whenever I see OH, that is an alcohol. So here, the alcohol is attached to carbon atom number 1, and we shall look at the naming I've told you in the next video. So this is butane 1-ol, because the alcohol is attached to carbon number 1, and here carbon is attached to carbon number 2, so it's going to be butane 2-ol. I've told you I'm going to look at the naming in the next video. So this video, you take notes about naming. It's about you understanding position isomerism. So position isomerism, the key takeaway in this is that the two compounds are going to have the same molecular formula and they are going to have the same functional group, but they are going to differ in the position where the functional group is attached. So that's the difference. So let's go to the functional group isomerism. Now we're saying that for the functional group isomerism is going to be when two or more compounds are having the same molecular formula, but they are going to differ in their functional groups. They're having the same molecular formula, but they're going to have different functional groups. And I've told you how to spot a functional group. I told you whenever you see in your table, which you drew earlier on, whenever I see this attachment, this is going to be a carboxylic acid. And whenever I see this is going to be an ester. So both of these ones, this is a different functional group and this is a different functional group. So they are going to have the same molecular formula, just like here, but they are going to differ in the functional groups. This is a carboxylic group and this is an ester group. So this is going to be propanoic acid and this one is going to be methylethanol. We shall be looking at the naming more or less. I know the naming is a problem to many of you. We are going to be looking at the naming in the next video. Looking at another type of isomerism, we have there are two types of isomerism. We have structure isomerism and stereoisomerism. And under structure isomerism, we have three main types of isomerism. We have seen chain isomerism, we have seen position isomerism, and we have seen functional group isomerism. So another type of isomerism, apart from the structure, we have what we call the stereoisomerism. And we are saying that in this stereoisomerism is when two or more compounds with the same molecular formula and the same structure formula, but having different spatial arrangements are going to be existing. So this is when two or more compounds with the same molecular formula and same structure formula. The other side, compounds are having same molecular formula but different structure formula. But here in stereoisomerism, they are going to have same molecular formula and they are also going to have same structure formula. So that's the difference. But where they are going to vary, they are going to be varying in their spatial arrangement, which we are going to look at. So stereoisomerism is categorized into two classes, and one of them is called optical isomerism. Now for optical isomerism, we are saying that this is when two or more compounds with the same molecular formula and the same structure formula, but they are not going to be superimposable on each other. It's going to be that situation in which two or more compounds are going to exist. They are both going to contain the same molecular formula and the same structure formula, but they are not going to be superimposable onto each other. And that's to say, one isomer is going to be the mirror image of the other. And with that, we represented it with a diagram. If you look at this, they are having the same structure formula and the same molecular formula. But if you look at this, each isomer is the mirror of the other. They are not the same if you look at them spatially. They have the same structure formula and the same molecular formula, but one of them is a mirror of the other. Otherwise, if they were the same, this black thing would have been the same as the other. So you're saying that they are mirror of the other because if you put here a mirror, you are going to get an image of this in this form. So that's why we are saying that they are not superimposable onto each other. And to explain that, you have said that one isomer is going to be the mirror of the other. So that's what we call optical isomerism, and it's under stereoisomerism. Looking at geometrical isomerism. Now for geometrical isomerism, it's going to occur where isomers occurs in isomers in which free rotation is going to be prevented by presence of a double bond. It's as simple as that. So whenever you're defining geometrical isomerism, always remember that it's a type of stereoisomerism where isomers are going to be prevented from free rotation simply by presence of a double bond. Now you're saying that these structures of geometrical isomers differ only in two configurations, and we are going to call those ones cis isomers and trans isomers. If you look at cis isomers, these have similar atoms on the same side of the double bond. So both of them, the examples are here. Both of them are having double bonds, but for trans means diagonal, cis means the same side. So that's why you're having bromide ion this side and bromide ion this side. We call this one a cis isomer. But for a trans isomer, you're having bromide ion diagonally and the hydrogen ions diagonally. So under geometrical isomerization, we can classify two isomers under it. We have trans isomers where atoms exist diagonally from the carbon to carbon double bond. And the cis isomers, similar atoms exist on same side, either up or down the carbon to carbon double bond. And I have said that geometrical isomerism is going to be that isomerism in which you are going to prevent free rotation of the isomers simply by the presence of double bonds. Take a look at some of the types of reactions that are going to be involved in organic chemistry. Now, first of all, we are going to be looking at reactions where we involve bond cleavage. Cleavage simply means breaking. Cleavage, you are breaking something. Now, you're saying that we are going to have a lot of cleavage in organic chemistry because we have to see how atoms of products dissociate to react with how atoms of reactants dissociate to react with other atoms of reactants that have also dissociated. So we are going to be showing you the process of dissociation and combination to form products. That's what we mean by types of reactions, and cleavage means splitting or breaking. So we are saying that a covalent bond can be broken in two ways. Now we have homolytic cleavage and we have heterolytic cleavage. Now what I want you to understand here, in homolytic cleavage, remember that these are bonds. A bond is composed of bonding electrons. For homolytic cleavage, there is equal sharing of electrons between atoms. Now notice that these bonds must be touching this bond that you have drawn. So if you're having two atoms bonding with each other, let me say X and T. If homolytic cleavage is to occur, we share electrons, but these bonding electrons, we share them. So one atom is going to take one electron, which is represented by a dot, and another atom is going to take one electron, which is represented by a dot. So you're going to end up with what? You're going to end up with C having a dot upwards. And what did I say this one represent? I told you this is a radical. Whenever you're having an atom having an electron upwards, it's going to be a radical. Plus, you also add on the X. Also, this X is going to have a dot upwards. And this is also going to be a radical. Now, if the atoms are of the same elements, let me say you had X here. Now, this one wouldn't be there. You have two radicals of X. So under homolytic cleavage, we share electrons equally. Each atom in that bond gives off one electron to the other. There are two electrons that are involved in bonding. So they share those two electrons, each one takes one. And whenever an atom contains only one electron, one unpaired electron, it becomes a radical. Now you're saying that, let's come back here. Homolytic cleavage, happens when there is negligible or no difference in the electronegativity of the two covalently bonded atoms. But you can simplify this definition according to the way you have understood. We mark your understanding, we don't mark exact definitions. Homolytic cleavage is where two covalently bonded atoms share the bonding electrons equally, forming radicals. That's very true. That's why we're proceeding here, telling you that this leads to formation of free radicals. So if you look at the chlorine molecule is written like this. So whenever chlorine is involved in a reaction, first of all, these atoms that make this molecule have to part. But if you look here, since both of them are chlorine atoms, they have the same electronegativity. So that means that they are going to share electrons equally. And whenever you're sharing electrons, let me represent this one clear here. In homolytic cleavage, whenever you are sharing electrons equally, you represent with an arrow that has only one side. So this one is like this. It is not a full arrow. And also this side, you add the other side this side. The arrow is like that. Don't write this one, which has two that forms a sphere. This is very wrong. This one shows that two electrons are being shared to that atom. But here, whenever you present only one, like here, you are showing that only one electron has come here out of the two bonding electrons that we have here, and which you want. So that's what is presented here. And I've told you are going to form two radicals, because to form a radical, we need only one electron upwards an atom. Now let's look at heterolytic cleavage. Now for heterolytic cleavage, this one is unfair. You find that one atom in a covalent bond situation, one of them is more electronegative than the other. So the one that is more electronegative than the other takes away all the bonding electrons towards itself. And whenever it takes away both the bonding electrons towards itself, it becomes negatively charged. In other words, it becomes a neutrophil. I told you a neutrophil is an electron-rich species. And the one they have took away electrons from, it becomes positively charged. And what did we say that positively charged species are called? They are electrophils. So electrophils is something that is positively charged because it's electron deficient species. They have took away its electrons, so it's need of those electrons back. Now you're saying that electrolytic cleavage is going to occur when atoms in a covalent bond situation, one of them is more electronegative than the other, and it's going to depend on formation of ions. So if you were to look at the compound of hydrogen bromide, now here you are going to use a full arrow. The full arrow you are going to use is going to indicate that now here hydrogen and bromine is more electronegative than hydrogen. So what bromine does, it takes out all these bonding electrons to itself with a full arrow. And what it does, since they have stored the bonding electrons of hydrogen, will form a proton or an electrophile of hydrogen, showing that they have took away its electrons. So it's an electrophile, it's electron deficient. They have took away its atoms. The one that takes the bonding electrons becomes electron rich, and therefore it becomes a neutrophil. Just like we defined, a neutrophil is going to be that component that is negatively charged because it's rich of electrons. They are saying that this is going to happen in this case because bromide is more electronegative than hydrogen. Therefore, it takes away all the bonding electrons towards itself. So looking at another type of reaction, you're going to be looking at the electrophilic addition reaction. Just like you have understood the definition of an electrophile, that is a species that's looking for electrons, or it's an electron deficient species. So that means that it will be looking for hydrogen or for electrons or species that are rich in electrons. And how did we call those species? They're either unsaturated compounds or they are neutrophils. So you're saying that an electrophilic addition reaction is going to be that reaction in which that electrophile is going to be added to unsaturated compound, and the moment we add it to unsaturated compound, we form a saturated compound. For example, You're having ethene reacting with hydrogen bromides gives you bromomethane. Now let's look at how this reaction takes place. So for this reaction to take place, the bond between hydrogen and bromine atom, it first breaks because I told you bromine is more electronegative than hydrogen. So it takes away all the bonding electrons with a full arrow. Now once it does so, we form an electrophile because we are going to form an hydrogen atom, which is positively charged. And always, its electrons, bonding electrons, always come for those electrophiles. So the bonding electrons that are present as a double bond, as one of the double bond, comes for that electrophile. Always remember that. Electrons go for electrophiles. The electrophiles can't go for bonds. It's only electrons that are able to move. So they are able, that's why this arrow is pointing this side, going to hydrogen atom. And then bromine takes out the bonding electrons and it becomes a neutrophil. That's why now after this bond coming for the hydrogen atom, it adds here. That's why we form CH3. And this, remember that one of the carbon atoms uses the bonding electrons to pull hydrogen towards itself, and that means that the other one is going to remain lacking a bond. That's why it becomes a positively charged carbon here and bromide ion here. Now later the bromide ion, I told you, it's electrons that move. Remember that this one is also an electrophile. So the bromide ion that has been formed, the electrons on it look for electrophile that is being left, which is our carbocation. So the electrons move towards that electrophile. I told you, it's always electrons that move looking for electrophiles. It's electrons that move. So arrows must be coming from either negative charged ions, or they must be coming from bonds, either double or triple. So you're going to form bromoethane. And that's the mechanism for that reaction. We are going to be looking for mechanisms more in details in the later videos. Now, if you look at the electrophilic substitution reaction, we are saying that this is going to be a reaction in which the electrophile is going to replace, just like you are hearing the statement, electrophilic substitution. An electrophile is substituting for an electrophile. So here we are saying that a reaction in which an electrophile replaces the hydrogen atom that is present on the benzene ring. And such a reaction is given by this. We react benzene in presence of methyl chloride and aluminium chloride, and we form taurine or methylbenzene. I've told you are going to be looking at this in details, but what we need to know is how these reactions are formed, and we get definitions from the given term itself, electrophilic substitution. Now here, electrophilic substitution is only undergone by benzene ringed compounds, whereby you are going to see that an electrophile is going to substitute for an hydrogen atom that is going to be present on the benzene ring. For the mechanism, the bond between the methyl group and the chloride ion is going to first break and attach this chloride onto aluminium chloride. I've told you are going to look at these experiments more in details on their topics. We are going to be looking at this in benzene. So we shall form an electrophile of methyl, and we also form a complex of aluminium tetrachloride. Now what the unsaturated bond in benzene comes and looks for the electrophile. I told you this is a full arrow. So it looks for the electrophile, and it's always electrons that move. So arrows must be coming from electrons looking from unsaturated compounds, or from neutrophils looking for electrophiles. So arrow must be going to the electrophile always. Now it's the methyl group comes and attaches here the hydrogen atom. This hydrogen atom is present on the benzene ring. So to make this carbon atom stable that has attained a positive charge, this bond breaks off inside and remain with methylbenzene plus our electrophile, which is hydrogen ion. But we don't leave ions unreacted in mechanisms. So this hydrogen ion comes and reacts with this complex that has been left, which is aluminium tetrachloride, forming back our aluminum chloride and hydrogen chloride. Now, if you look at nucleophilic substitution reaction, it's going to be the nucleophile substituting an atom or a group of atoms. Just like you're hearing the term nucleophilic substitution, a reaction in which the nucleophile replaces an atom or a group of atoms, forming a compound with a different functional group. Now, this one occurs mainly in alkyl halides, and this mechanism is not suitable for me to be explaining it to you if you're just starting chemistry. But however, you can write it for the cases of taking notes and you understand it later. So just to simplify, for those of you who know mechanisms, sodium hydroxide starts by splitting and they form the respective ions because sodium hydroxide is a strong base, so it fully ionizes to give us sodium ions and hydroxyl ions. The bonds break, giving us the electrophile and the nucleophile. We don't leave unreacted ions in the mechanism, so react them to form back our compound. Nucleophilic elimination reaction is going to be that reaction in which a nucleophile is going to eliminate an atom or a group of atoms from unsaturated compounds. And the example we gave here is alcoholic potassium hydroxide being heated with an alkyl halide, giving you an ethene and potassium iodide. And you have looked at this mechanism already. So first of all, we start by reacting what we are having on the arrow. So the base reacts with an alcohol to form a solid. Now this solid is strong, or it's a strong ionizing solid. It fully ionizes in solution to give you the respective ions, both a neutrophil and an electrophil. So what the neutrophil does, we form a kind of electrophil here. So this neutrophil comes for this hydrogen. Now this bond on the hydrogen breaks back to form the double bond. And this, first of all, is this alkyl halide that breaks off first. So we form our propene and iodide ions, but we don't leave ions unreacted in a mechanism. So these iodide ions react with the potassium ions to form potassium iodide. I've told you, don't worry about the mechanism. We are going to be explaining them further. Looking at one of the final parts of this episode, introductory episode, we are saying that we are going to be defining empirical formula. Now we ask these definitions, surprisingly at A level. Empirical formula is going to be that formula that shows the ratio of the atoms of the elements that are present in the compound, but it is going to be showing their simplest ratio. However, the molecular formula is going to show the exact number of the atoms of each element in the formula of any compound. So you have to master these definitions because they are highly examinable. Now we are seeing that combustion analysis used to determine empirical and molecular formula. Now you're saying that when an organic compound is completely burnt in oxygen, only carbon dioxide and water are formed. Remember that most of the carbon compounds we have, they are composed. Now we are going to be telling you that a carbohydrogen or a carbon hydrogen compound, whenever you hit a carbohydrogen or a hydrocarbon, we get only carbon dioxide and water because we are hearing hydrocarbon, hydrogen and carbon. Whenever you hit them in oxygen, you are going to get carbon dioxide and water only. Now here I gave you questions to try out, and each question I gave it an answer. So you try them out with your friends, you discuss them and you take them to your teacher for guidance. So you take the questions and you discuss them as your group and you take them there. I gave them the answer you should get. Now when you don't get this answer, you go back and you discuss it with your friends. If it fails to come out, then you advise to see the teacher, because I'm not supposed to look at organic calculations in this introductory video. In fact, they are supposed to be looked at the introduction of physical chemistry. So what I gave here, I gave you questions to try out, and I've given you methods you are supposed to use, and also the answers you are supposed to get. So whenever you're going to be given masses, I've told you, discuss this with your friends and try to see Are they coming out? And if they're not coming out, try to see a teacher immediately, so that that teacher will guide you throughout the questions. Now there are some calculations where the formula of the compound is going to involve explosion with oxygen, and they're not going to specify whether it's hydrocarbon. Sometimes they specify, and sometimes they just tell you that they just give you volumes. Now for such equations, the only disturbing part are the equations. You should know the equations that are involved. I've told you these calculations must be in physical chemistry. And this is the one where they give you that the compound is in this formula, which is very rare, and we are examining it. So you make sure that you master it. So these are the questions involved for such approaches. Each question has an answer. Each question has an answer. And whenever you don't get that answer, try to see your teacher immediately, or discuss with your friends. Some of your friends may have the idea, or may have a better understanding of the topic more than you. Brings us to the end of this video. We start in the next video of organic chemistry, which we are going to start with alkanes and alkenes, and we are going to be looking at mechanisms, nomenclature, and everything, properties and reactions. So share the video to your friends so that you can all benefit as a family. See you in the next video.